Templot uses prototypical geometry of points and crossings to produce its templates. And without knowing the basics of this, it's difficult to make good use of the Templot facilities. So I'll move to sharing the Templot trackpad screen, and we'll continue from there. So this is an ordinary left-hand turnout. The main road is straight, the branch road is curved. And in the prototype, this is constructed of 3 units. The switch unit at the toe of the point has the switch blades, which actually move. At the other end, the crossing contains the intersection of the gauge where the roads start to diverge. And in between are the closure rails that join the 2 units. Let's have a little look at the switch unit to start with. So the switch consists of usually a very short approach track, maybe a couple of sleepers, and then the toe of the point is marked by the start of the moving switch blades, which are then continuous up to the end of the switch unit. Logically enough, called the switch heel. These cross hatches mark the end of the rail joints in the prototype switches. The switch rails are planed over part of their length, indicated by this white crosshatch on the Templot template, down to their tips, where they are effectively feathered to about 3/8 of an inch wide in the prototype. In 2mm scale, this equates to about 2.5 thou of an inch, or just over 0.06 millimeters. That is still a significant thickness in the real thing, and some companies, notably the GWR, would joggle the stock rail to accommodate it, so that if a wheel was approaching in the facing direction, there was no risk of the flange hitting the end of the switch rail. Templot provides for joggles. We'll just enlarge that so that you can see the effect of it. By the reel menu, switch settings, this box here, joggled stock rails. So just look at the effect of that at the tip of the blade there. The joggle takes about 6 inches of length to achieve, so there is no risk of a hit coming in the trailing direction. The switch rails may be pivoted, particularly older ones, pre-grouping and early grouping, would be pivoted at their joint with the closure rail here. But in the grouping period, the Railway Engineers Association developed a set of standards that were used increasingly across all the companies, except again the GWR, who were late to adopt them, of the so-called semi-curved flexible switch. And this is the most common type of switch that would be appropriate to use when modelling bullhead track. The heel of the switch would be anchored by at least 2 chairs which were fixed, and then the rest of the switch would be free to flex, moved by the stretcher bar indicated here. The ends of the switch rails, which nestled against the stock rail, were planed straight and flat for the REA semi-curved switches, so that approaching in a facing direction, there would be a change of angle from the approach track to the planed part of the switch. This switch has now been changed to a B switch, so a sharper switch, and this just illustrates more clearly the so-called set. And at the angle of the set between the approach to the toe and then alongside the planed switch rail, that angle there matches exactly the angle of planing in the switch rail. I'm just going back to the D switch again. From the end of the planing to the end of the switch rail, the rail was curved, hence the name semi-curved. The length of the planing would vary depending on the acuteness of the switch, and there were standard geometries for these named by letters. An A switch had the shortest planing and therefore the acutest angle, through B, C, D, E, F, and in more modern times, longer length even than the F switch for today's high-speed trains. The whole length of the switch and the radius of curvature would also be defined by the letter. And again, the A switch would have the sharpest radius of curvature, getting progressively more shallow as you go through B, C, D, E, and F, and so on. The GWR was unusual in that the planed length of its switches for a long time was curved, so that there would be a smoother curve through the whole switch. There wouldn't be a straight section and then a curve. But that did not necessarily mean that the radius of curve over the planed section and the free section was the same. There are other geometries available for switch settings. Some are older, some are newer. Some are applicable to flat bottom rail rather than bullhead. And Templot holds files for many of them in its switch menu here. So these are the semi-curved flexible REA switches, the standard switches through grouping and BR period for bullhead track. A, B, C, D, E, F it goes up to. The GWR held out with curved switches, and Templot has the common ones for there too. If you need a switch that's sharper than the B curved flexible switch that the GWR used through the grouping period, then they used their older form of shorter planed switches. And if they needed one longer than a D, then they had longer ones too, a 30-foot straight heel switch. Going back further, switch rails were often pivoted at the heel rather than rigidly fixed, and these are provided here in Templot 2 with a straight heel switch. So the switch blade would actually be straight even for a curved branch road. Various options for flat bottom here. Templot has also defined 3 sharper switches for modelers. Very often we're more constrained by space than the prototype. They work, but they're not strictly prototype, they'd be too short. And the switches that were used for slip roads were also different to those used for turnouts. They were shorter and sharper. And Templot has tailored them down to the planed lengths of the switch and stock rails that are needed to be added to the diamond to make the slip. Similarly, switches could be different for tandems too. This would be related in part to restricted spaces between the rails for chairing too. We don't really worry about putting chairs on our Templots in 2FS, but in larger scales, you may well do that. And finally, you can define your own switches and save and store those in these custom files here. Let's move now to the crossing, the so-called common crossing or V crossing. The actual crossing is formed of 2 rails that are planed and spliced together, and 2 wing rails which continue the closure running rails up to the crossing where they diverge. The check rails prevent the flange on the other side fouling and mounting the point of the crossing and mistracking through the point. There are two features of the crossing which it's important to know about for Templot. One is the angle of the intersecting tracks, the angle at the tip of the V, and it may well be different just proximal to it and just beyond it. The angle is described not in degrees, but as a 1 in 6 or a 1 in 7, which means that for, say, a 1 in 7, every 7 units along the track here, the branch line diverges by 1 unit. In broad terms, 1 in 5s would only be used in the tightest curves in dockyards, goods yards, and so on. 1 in 6 would perhaps be the sharpest angle found in normal station yards. Running lines where a reasonable speed would be achieved, it would be a 1 in 9 up to 1 in 12, 15, or even higher. The higher the number, the shallower the angle. Templot predictably allows you to change the angle in steps. And again, it's the real menu, V crossing options, V crossing angle. So this one happens to be a 6.93. There's a reason that I did that, which we'll come on to in a minute. If we change that to a 8 or 1 in 8, you can watch the difference, the effect that has on the angle here. Much shallower, and you can see that the lead, the length from the toe of the point to the crossing, has increased. It's a longer point. I'm just going to go back to that V crossing angle. The other feature that Templot allows you to alter is the curvature through and beyond the crossing here. And Templot defines 3 crossing geometries here. If we come into real V crossing angles, we see that this is curviform. The other options are regular and generic, and we'll just have a brief mention of parallel at the end. In a curviform crossing, the radius of curvature through the closure rails is continued right through the crossing and beyond to the end of the crossing unit. And these crosshatches mark the end of the construction of the prototype crossing unit. So that's a smooth curve right through the crossing. And that would be employed out on running lines. The generic crossing, and when I hit this, just have a look at what happens to the angle of this turnout road here. It apparently reduces the angle, but in fact, the angle at the crossing tip here has remained the same. All that's happened is that from this tip onward, the branch road has become straight, not curved as it was in the curviform. So in this so-called generic crossing, there's a constant radius of curvature through the closure rails up to the fine point of the crossing marked by this white cross line. So we're curved up to there, and then from there on, we're straight. So the geometry is identical between the toe and the point of the crossing. It only alters on the branch track after that. Regular takes that even further by extending the straight section further back into the crossing so that it's straight through the whole crossing. In fact, from this, it marks the line here where the straight starts, and you can see that here. So the lead, i.e. the length from toe to fine point in a regular crossing is even shorter than that of a generic crossing. That can be useful if you need to achieve a particular angle in a more constrained space. The regular crossing would be routinely used where there is a crossover or a reverse curve immediately after the point. If the road was coming back to run parallel, for instance, or was part of a crossover between two tracks. The reason for that would be to introduce a longer straight section between the two curves of the points and prevent an immediate and quite sharp reverse curve. We'll just reduce that and take it out of the way of the menu so that you can see the effect. The peg is at the toe of the point here, so that remains fixed. So all the changes will occur at this end. So this is regular. If we go to the intermediate one, generic is really intermediate between the regular and the curviform. That's the generic. The curve is extended further up to the crossing point, marked here. Curviform, all that happens is the curve continues through into the branch. It apparently gives a sharper angle at the end of the crossing because the curve is continued on through the track beyond the fine point, but the crossing angle at the fine point remains the same. One other thing that Templot allows you to do with the regular crossing is alter the length of the straight approaching the fine point. And that again you can find under Real, V-crossing options, V-crossing settings. We've got the regular crossing here, look. The default is to automatically determine the length of the straight through the crossing according to the V-crossing angle. If you click this fixed at button and then say OK, it allows you to adjust the angle of the V crossing and then fix the length of the entry straight. Now that's got it as 6.93 millimeters. Let's bring it down to say 12 millimeters and see what effect that has. And we're looking at this area here. And you can see that this marker line here showing where the straight starts has moved this way. The effect of that, of course, is to sharpen up the radius of the closure rails and shorten the lead, the length between the toe and the crossing. So going to a regular crossing and increasing the approach length of the straight to the crossing is a way of shortening the length of your turnout if space is tight. Now, everything I've said about the different crossing geometries apply to the point I was demonstrating on, that is, where the main road is straight. And I use that as the example because it's easier with that to get the concept of the different geometries. It isn't quite that simple when the point is curved. So here is a new template, plain straight track. I'm going to put a turnout on it. I'm going to roam that along a little bit. And I'm going to make this a rather bizarre turnout. I'm going to make it a C switch. with a V5 crossing angle, which it already has. I'm going to extend the turnout road because that will show us what happens to the curvature on the turnout road better. So action, mouse geometry, turnout road exit. And I'm just going to check that this is a regular point. Actually, something I have learned today from browsing the Templot help tutorials is that there is a box up here that has a green R in it. That R indicates that the geometry of the crossing in this control template is regular. If I switch that geometry to curviform, it has become C for curviform. Similarly, if we make it generic, it's become G. And just to complete the set, parallel is P. You live and learn. Back to the main thread. So we'll make this a regular crossing. And we'll re-establish the turnout road exit. There's one other amendment I'm going to make the effects I want to point out more obvious, and that is to extend the crossing approach straight. Remember, this white line marks the point at which this regular crossing changes from the curvature of the closure rails to the straight geometry through and beyond the crossing. The easiest way to do that is through the template menu, V-crossing settings, switch from auto fit for the crossing length of entry straight to the fixed at. Okay. Now 30 millimeters is very long for the entry straight. That was what I was playing with before I started this recording. So we'll apply that to this crossing. And you can see the impact of that. So we have a bizarre point here, but it will illustrate the point. Here's the switch, a C switch, quite shallow. The crossing starts here. The entry straight starts back here, which means that the length of the curved closure rail can only be between the start of the entry straight and the end of the switch. So a very sharp radius of curvature here, and it points up very nicely the three different components of the point. So this is the situation for a regular crossing on a straight point where the main line is straight. And from the start of the crossing entry straight, the branch line is straight, approaching the crossing, through the crossing and beyond as well. Now, if we start to curve the main line, and this will introduce a constant radius into the main road through the point. Just bring this up a little bit. The main line will always do what you tell the geometry to do. So we've told the main line here to curve to a constant radius, and it has done that. It will then design the rest of the point around that to maintain the geometry of the C switch and of the regular crossing and the prolonged entry straight to it, the 30 millimeter entry straight. But you can see now that quite definitely what on a straight point was a straight road through the crossing for the branch and beyond is now curved. And that is because a straight branch road through a regular crossing is a particular case, and it's particular for when the main road is straight as well. In fact, what defines a regular crossing is that the curvature or the straightness of the road for the branch and the main road through the crossing and beyond are the same. So when it's a straight road, both are straight. That's nearly straight, isn't it? When the main road is curved, then the branch road becomes curved to the same radius as well. And you can see that quite clearly here. And you can see that the radius changes sharply when you reach the line previously we were calling the start of the entry straight. So that's just a little complication really for the regular crossing. If you put a regular crossing into a point which has a curved main road, the branch line through the crossing and beyond will not be straight, but it will be curved to the same radius as the main road. The same principle applies to the generic crossing, except that the start of the entry straight is moved up to the fine point of the crossing. So the radius of the branch road from that point onwards is the same as the main road. But in this particular case, the closure rails are much longer, so they've been able to adopt a much shallower radius of curvature to join the switch to the crossing unit. Now, when you go into the crossing options in Templot, there are the three geometries that we've already talked about: regular, curviform, and generic. And there's also the fourth, a parallel crossing, which I'll briefly try and explain now. Let's start with a new template, which will make B8 straight point, a standard modeler's point, in other words. And I'm going to make the crossing here curviform to start with. Now, the parallel crossing is not a distinct crossing geometry in its own right. It's a Templot construct, really, which is a convenience. It saves a little bit of time for a particular purpose. The parallel crossing does two things. Firstly, it makes the crossing itself the same geometry as a regular crossing. And secondly, it adds a return curve to the branch road so that it swings back parallel to the main road, and it will stay parallel with the main road and to the same length as the main road, irrespective of whether the main road is straight, constant radius, or a transition curve. So as I said, this is a curviform crossing just at the moment. So if we enlarge that, and I now convert this to a parallel crossing, you should see the introduction of an entry straight leading up to the fine point and a straightening through the crossing and into the branch track. So let's do that. We'll do it through the template so I don't cover it up with the menu box. We'll go into the V crossing settings there. So we'll go up to a parallel crossing, and when I click OK, see what happens to the geometry here. So we now have an entry straight marked by this construct here before the fine point. And the branch track is starting to curve. I'll just reduce this a little so we can see what it's doing. It's extended the main road and it's added in a branch track as well with a return curve, and it's extended both until the return curve is now parallel and tangential to the direction of the main road. So if I reduce that again, the other thing that happens with a parallel crossing is that the main road and the branch road are irretrievably bound together at whatever you have set the track centers to be. I didn't define that setting here, so it's defaulted to the standard 6-foot way. But if I extend, both extend. If I shorten, both shorten. You cannot separate the branch and the main road at all for any function, for any individual manipulation in a parallel crossing. If I curve them, they both curve together. And if I make them a transition curve, come to the geometry transition curve, let's have an easement from straight. So we're straight at the start here. There's the transition zone. There's the fixed radius curve beyond that. So we'll just manipulate the transition zone a bit so you can see what happens. Mouse actions, geometry, move transition start. We'll move that down and we'll shorten the transition length as well. And you can see that the branch and the main roads always move together and remain parallel with that same 6-foot way all the way along. And if we move the transition start, you can see that. So that's the parallel crossing. Not really an individual crossing geometry in its own right. It puts the crossing geometry to regular and it adds a return curve to the branch, and the branch and the main roads remain parallel and irretrievably linked. It does have its uses. For instance, if you're wanting to make a fan of parallel sidings in a goods yard or in a fiddle yard, but it has its limitations because you can't do anything individual with the branch or the main road. I'm just going to finish talking about V crossings here by flipping between the regular, curviform and generic so that you can see the difference. And the reason I made it such a weird crossing angle of 6.93 was because for the curviform crossing, the point of the crossing lay virtually on this grid line here. So it was easier to see the impact of the geometry here on the curves through the crossing and the length of the point. Remember, the toe is fixed. So that's regular. That's generic, and the generic crossing nose is exactly on the grid line. We wouldn't expect that to change for the curviform because the anatomy of the crossing up to the fine point of the crossing is the same as the generic. But the curve continues on through this short stump of the branch road that is part of the crossing. We might have started out in our railway modelling career by talking about 2-foot radius, 3-foot radius, 4-foot radius points. But we now realise, of course, that the course of the road through the point is not constant at all. There is, whatever the curvature or straightness of the approach track is, then there is the angulation into the planed section of the switch. Then there is whatever radius is determined by the rest of the switch geometry, whether it's an A, B, C, or D. Then there is a different radius, very often through the closure rails, which may or may not continue through the crossing, which can be curved or may become straight again. It is possible to combine any switch with any crossing, but you may not get a geometry which is viable. This is a weird one. Okay, it's as near as, damn it, a V7, a 1 in 7 angle, but it's got a very long switch, a D switch. I've chosen that so that you can see the effect of the straight approach, the slightly angled but straight planing, then a shallow curve through the switch. It's a large radius switch, and then a sharp curve through the closure rails, which has continued on through the curviform crossing. You can see that quite clearly. It becomes much less apparent if you match the length of the switch to the sharpness of the crossing, and that is what was done prototypically. So an A crossing would tend to be matched to sharp angled crossings, 1 in 6, 1 in 7. A B switch would most commonly be found with a 1 in 7, 1 in 8, a C switch with a 1 in 9, 1 in 10, D switch with a 1 in 12, maybe 1 in 15, and so on. And for each switch, there is one particular combination, which is known as a natural point, where the radius of curvature of the switch is the same as that through the closure rails and crossing, if that is curved too. For an A switch, the natural point is an A matched with a 1 in 7, an A7. For a B switch, it's a B8. For a C switch, it's a C10. For a D switch, it's a D12. For an E switch, it's an E16. We'll just go to a common modeler's switch, say a B8, shall we? And we can see the difference there. So V crossing angle, we'll make that an 8. The switch, we will make a B. You still have the straight section through the planing, but then the curve from there on is smooth with a constant radius all the way through. Think of the closure rails as rails of convenience. It's the switch geometry and the crossing geometry which define the point, and the closure rails do whatever they need to do to give a smooth road from one to the other. Likewise, the main road will do what you tell the main road to do, whether it's a transition curve, a straight, a constant curve to left or right, that will be smooth through the main road. The branch road from switch through closure rails and crossing and beyond will do whatever you tell the point geometry to make it, whether the switch is an A, B, C, D, E, whether the crossing is a 1 in 5, a 1 in 7, or a 1 in 20. The third element of crossings, just to very briefly have a look at, is the so-called K crossing or obtuse crossing or elbow in the center of a diamond or a slip. And again, that would be built up as a separate unit by the crossings shop, and the limit of the crossing is shown here by these crosshatch marks on the rails. So if you asked for an obtuse crossing from your track making shop, that would be what you would get. The anatomy is quite different. The chairing is very different, with specific chairs at the center and at the tips of the closure rails here. As I said, we don't worry too much about all the different chairs in 2mm. Now, that would be a single unit in the prototype, but in Templot, a diamond is built up from two half diamonds which extend as far as the midpoint here. So a half diamond in Templot would be this. And you need two of them to make a diamond or a slip. The one point to make here, and this is particularly relevant if you are making an irregular diamond by hand rather than by using one of the automated menu options, is that the angle at the K crossing of one half diamond has to be identical to that of the other one. Otherwise, you will introduce a sharp angle between the road approaching the centre of the crossing and leaving it, which obviously would not have happened. Even where a diamond was on a curve or where both roads were curved, the angle at the centre point was the same on both sides. It may be different to the V crossing on one side, and that may again be different to the V crossing on the other side if it was an irregular diamond. But the two centre ones would always be the same. The V crossing options in a diamond are exactly the same as those in a turnout, with the same geometry options, same angle options. Another point to make about the obtuse crossings is that they were commonly 1 in 5, 1 in 6, 1 in 7, 1 in 8. They could be shallower, but you can see that there is a limited option for checking the rails as they go through the crossing, to the extent that if you have a shallower crossing than 1 in 8, the wheels can't be properly checked, leading to the risk of hitting the tip of the crossing rail here and derailing. And for obtuse crossings of 1 in 9 and above, that is shallower than 1 in 9, you would have the so-called movable crossing, where the point of the crossing rail here would be longer, would come right up to the middle, and would nestle against the stock rail, and would be switched just like the switch of a turnout is switched to accommodate one track or the other. To illustrate a movable crossing, we have to remake the diamond to a shallower angle. So we'll delete that half diamond, we'll make that half diamond the control. We will alter the angle of that K crossing. Let's make it a 10. We now have an irregular diamond with the K crossing a 1 in 10, the V crossing 1 in 7. So we need to adjust the V crossing angle too. Now let's see if we can make a diamond of it, which we have. And you can see that without asking it, Templot has actually made that a switched diamond. It's extended the crossing rails right up to the center point of the K crossing. And when you would come to build this, you would need to introduce a stretcher bar between those two and move those just as if they were switch rails in a turnout. You do also have the option of telling it to make a movable diamond, a switch diamond, there. If we make it a fixed diamond, it will do it for this angle, but there would be a massive risk of derailing, because I think you could see that the wheel flange, when it's level with the tip of the crossing rail here, is not checked on the other side, so it could easily mistrack. So that's a brief introduction to the geometry of points and crossings. I hope enough to allow you to make full use of the options that Templot provides.